and also NSF, not only financially, but also, we have several program directors here. Dr. Robert Woolman from ARO, and Dr. Huayu Dai, and Yifang Huang from NSF. So we'd like to thank them for both supporting us and also for being here. So next, I'll ask Professor Moss-Cavey to say a few words to welcome you on behalf of the University of Minnesota. So Minnesota provided the space and also financial support for this workshop, and also staffing. So Professor Cavey was a former chair of the ECE department and also dean for the College of Science and Engineering. So Moss.
Thank you very much, Cheng Dao, and I add my welcome. Again, wonderful to see everybody here on behalf of the University of Minnesota. Again, welcome you to this really important topical workshop. It's a workshop talking about the confluence of data, signal processing, communications, and networking, and dare I say, AI sort of mixed in there. It reminded me of a conversation I had, Yorgo, I haven't told you this, but when I was just looking at the data-driven signal processing, it reminded me of a conversation I had many years ago with David Brillinger at Berkeley. I was in his office in Berkeley and walked in there, and Professor Brillinger, who I'm sure many of you have seen his books and so forth, I mean, he was sitting there with just reams of printouts, for those of you who know what computer printouts are. Anyway, so we were talking about, of course, back then, a lot of people in this room were involved in spectrum estimation and modeling and things like that. And so we were chatting about it and what was happening in signal processing in that area. And David said, you know what the problem is with you guys? So what? He says, you worry too much about theory. And this stuff is all about data. Look at these printouts. The printouts were, of course, reams of data, printout of data that he was analyzing. So we've circled back. Now we really have a combination of all of these. We are worried about data. We do take advantage of data very heavily in all the great theoretical work and algorithmic work that is done within signal processing, within communications and networking. So this is an extremely important topic. And before I sort of wrap up, let me again thank you, add my thanks to all of you who've taken the time to be here. I mean, this is a tremendous group. We're all looking forward to your wisdom, your ideas during the workshop. I also want to add my thanks to the National Science Foundation, the Army Research Office, for your support. And of course, we're here because we're going to be also celebrating the work of our dear colleague, Georgios Giannakis. Yorgo is actually the catalyst for this workshop. So because of that, I'm going to ask Yorgo, if he doesn't mind, just to say a couple of words to get us going.
Thank you so much, Moss and Cheng Dao, for the kind introduction. I don't have too much to add, except to thank everyone for taking the time and effort to come to Minnesota and celebrate this nice event with a workshop that is followed up by the Satellite Symposium. And I will add on what Professor Cavey said, Moss said, that I didn't know the incident with David Brillinger. But for those that perhaps the younger guys, David Brillinger accomplished statistician and theoretician, took his best student, arguably. And it was David Brillinger who introduced me to higher order statistics, and I happened to have met him in a workshop that took place where me, as a fresh assistant professor in Virginia, it was here in the Institute of Mathematics and its Applications. I met David Brillinger, and we played soccer later on at Berkeley, but originally we met here in Minneapolis. Okay. Once again, I also want to add one more thing, that the structure of this 1.5-day workshop is inspired by another simple fact that if one wants to cluster the research that we carried out with my group at the University of Minnesota, then you will cluster it under signal processing theory and applications, wireless communications, and networking with recent trends on data science and network science, including smart grid and social networks that the next speaker is going to introduce us to. So, once again, pleasure to see you here. Enjoy the workshop. Just an announcement over the weekend. There are interesting things to do in Minneapolis. You have sightseeing suggestions and so on. Thank you for coming.
Thank you, Yoko. So next, I will just invite Anatharam Swami. So he has been a long-term friend and colleague of Professor Janakis. So I'll ask him to chair the first session. Anatharam.
Yeah. Thanks. Great. But the 2 minutes out here, it's a privilege to share the session on higher order to filter banks to data-driven. For Ali and for, I guess, really great weather, 80 degrees today, right? I think it's the 60s, so enjoy the sunshine. So with that, let me introduce our first speaker, the high notes talk from, don't quite know what he's called, but maybe he's called doctor, engineer, professor, Dana. So I was going to have a quick sheet of things to say about Ali, and then I realized I probably need a notebook. So I'm just going to say a couple of things. He's probably lectured, taught in every continent in this world. Maybe not Antarctica, but I guess that's coming soon as well. He's a triple fellow, IEEE, USF, AAS, Shannon, Nyquist. He got all those awards as well. So let me not take more time introducing him. Let's give Ali a round of applause and welcome.
Sorry. Thank you very much, Anas, for that introduction. And I'm very, very happy to be here today. Okay. Maybe I should hold it in my hand. I'll hold it in my hand. Let me try it. Okay, so I'm very happy to be here. Okay, this is a special occasion. I have many, many good friends here at Minnesota. Actually, one of my very first workshop as a student was here when I came with my advisor, Professor Karas, to a workshop, a course at the Institute of Mathematics. And since then, I have had excellent colleagues, Nikos, who's sitting here, Yorgos, Moss, and many, many others. So thank you very much for inviting me. I do appreciate it. I'm going to give you an overview of some of the work we have been doing over the last maybe 15 years. It's work that has progressed to a point that I feel comfortable about. And of course, this is not a technical talk, so I will keep it at, I will not delve into theory, but just intuition, motivation, why the results are useful, why this topic is interesting. Okay, so before I start, just a brief comment. Okay, Moss talked about data-driven research. So people who have been doing adaptive filtering, and you have a giant of the field sitting here, John Treichler. Adaptive filtering is data-driven signal processing. That's how you train your filters, right? We have been doing it since the 1950s or 40s, perhaps, right? So signal processing has contributed a lot and added theory on top of it, right? Okay. So before I continue. So this is not working, okay. Okay, it's not moving. It's okay, I can. Okay. So before I move on, unfortunately, I will not be able to be at the dinner tomorrow. I know that this is a special event, and it was called here to commemorate the achievements of one of the key pillars in our field, in signal processing, in communications, in networking, including in the domain that I will be talking to you about today, okay? This is an image from 20 years ago almost, okay? You looked younger. Me too, okay? So, okay. Many of you know about contributions of Yorgos, okay? He not only contributed, this is a person with an H index of 160 plus, right? So that's an amazing status, right? Besides graduating many fantastic students, many of them accomplished faculty members, and many of them are sitting here, postdocs. Okay, so we are talking about a special individual in our community. So congratulations, Yorgos, for all these achievements, okay? So moving on. This is a brief outline of what I will be talking about. I may not be able to cover these topics, but at least I will give you an overview. Okay, so let me start with some motivation. Okay, so there is no question that information sciences, and by that I mean signal processing, communications, control, optimization, I blend all of that, applied mathematics under the term information sciences. It has progressed significantly in the 20th century with many, many famous names making impressive contributions to the design of standalone systems, control systems, inference systems. And here are some contributions, for example, to prediction and inference theories, and I list there many, many names. All of you recognize these names, and many of them are associated with our field, right? And then if you go further, even in control and optimization theory, there are some famous names. All of them have contributed to the advancement of the field in the 20th century and brought it to a very, very important juncture where now we can jump and move on to the next level. But most of these works have focused on designing standalone systems, okay, systems that operate on their own, okay, and perfect the design of these systems. But today, we are witnessing the emergence of networked systems in many, many domains, okay, and here I have examples. And what are these systems? These are systems now consist of multiple single-agent systems working together, trying to solve a problem, working against each other, trying to make it more difficult for you to solve the problem. Okay, so networking can happen at different levels. And these are examples of network systems, social networks, robotic swarms, autonomous systems, Internet of Things, edge computing. These are many, many, many examples. Today, I will focus on parts of adaptive networks, which is a topic that we have been working on for some time. The interest here, I would like to be able to design a networked system that has adaptive abilities in it, learning abilities. So I would like the system as a whole to be able to learn, to adapt, to sense the environment and do something in a more intelligent way. Okay, so that's the context, and that's why I refer to these as adaptive networks. Okay, so now these decentralized systems, they need to have certain properties. Okay, they need to learn from experience. They need to interact with humans. They need to perform complex decisions, self-repair when something goes wrong, adapt to changes in the environment. So these are some features that were not included in the single-agent design theories that were developed during the last century. These are additional interesting challenges that we have to So if you read the literature and if you look at the contributions of people working in this domain, including here, you're going to see that a new engineering science is emerging. A science that's able to account for the coupling that occurs between these interacting agents, because these agents, when they interact, they influence each other to the good or to the bad, and you need a theory to keep that under control. Okay, so this is a new engineering science related to networked systems, which needs to be developed and needs also to take into account the intelligence that you have in the loop, because these agents are not dumb. Okay, each one of them has its own interest, and then you would like these systems also to be able to multitask, to respect privacy, to be explainable, to be robust if some link or some edge breaks down, and so forth. Okay. And there are many advantages for working on networked systems like this. I list some of them here. For example, they operate on their own. There is no need for a central processor, because if that processor breaks down, the entire system breaks down. They are robust. If one agent dies, you still have the remaining agents who can continue to do the work for you. Okay, there are more respect for privacy, because you don't need to share the raw data. You can share only processed data. There are many, many reasons why working with networked systems is advantageous. Okay, so this is just a list of that. Okay, now when you work on network systems, you need to have a mathematical notation. You need to have a way to model interactions over these systems. Okay, and there are many mathematical tools that come into play in the context of studying network systems. This is one of them. Graphical models, but there are others. Okay, graphical models are not new. They have been around for a long, long time. I give you some references at the end of this slide. Okay, graphical systems consist of nodes that are linked by edges, and the links mean that these individual agents interact with each other, and the strength of that interaction is controlled by the weight you have on these edges. So graphical models like this are not new. Okay, so let me give you a more mathematical definition of what we mean by a graph. I mean, what you have there, I have a collection of agents that are numbered 1, 2, 3, 4, 5. Each one of these agents may have an individual risk function, cost function, or objective. I call it P sub K. And if you have individual agents, let's say L and K, they will be linked if they can share information between each other. They will not be linked if they cannot share directly information. And on the link, you have weights AKL for information from K to L, and ALK to weigh information from L to K. And what these weights mean, you can assign different confidence levels. I trust node L, but node L trusts me less. So the weights don't need to be symmetric, okay? So this is in general, and then every agent can have a neighborhood. Like agent K there is connected to L, N, 9, and 8, so that's the neighborhood of agent K. And we assume that the graph is connected, okay, and that you have at least one node, like node 4, that has a self loop. What a self-loop means is that you have at least one agent in your graph that has some trust in its own data. Because if no agent in the graph has any trust in their own data, then you have a very suspicious graph. Okay, so let's assume for the time being, so this is called a strongly connected graph, okay? And strongly connected graphs have been studied for a long, long time. There are books written about this. Okay, so for example, let me just represent it mathematically so that you understand. If I take a matrix A, okay, at every entry of this matrix, let's say LK, you put the weight on the edge linking L to K. That becomes the mathematical representation, matrix representation of graph. So connected to nodes L, 7, 2, and 6, they have weights reaching them, and we assume that these weights add up to 1, so that every agent can combine the information from the neighbors in a convex manner. Okay, so this is a standard assumption. We refer to matrices like this, where the columns add up to 1, as left stochastic matrices. The columns add up to 1 and the weights are non-negative, okay? So this is the model, and matrices like this have been studied for a long time. There is a very famous theorem, the Perron-Frobenius theorem, which guarantees the following. Matrices like this have an eigenvalue at 1, and this is obvious because of left stochasticity. But what's more interesting is that if you look at the eigenvector associated with 1, all its entries will be positive and they add up to 1. This is not true for any matrix. It's true for left stochastic or doubly stochastic matrices when both columns and rows add up to 1. Okay, so this is called the Perron vector. AP equals P, so the eigenvalue is 1. The entries add up to 1 transpose and P is positive. This vector plays a very, very important role in quantifying the performance of networked systems, okay? Because every entry P sub K tells you how important that node is to the inference problem that you are trying to solve, okay? Now, this is not exactly what I will be talking about because we need to go a step further. You see, graphical models like this have already been subsumed or covered by the traditional theory of state space models. You know, look at this state space model. You have a state X at time n with entries X1 through X6, and then the state at time n minus 1, and then plus some driving input, which I call the vector H. You can transform a model like this into a graphical representation. You see, if you look at the first row, so the state X1 depends, if you look at the locations of the X's in the first row, depends on state X1, state X3, X4, and X6. And then you add links there from 6, from 4, from 3, and 1, and then you have an input H1. So classical state space theory already has this representation embedded in it, okay? And you have under the graph there the updates written in terms of classical state space form, okay? Now, to design adaptive networks, we need to go a step further, okay? Because these models do not account for individual learning and dynamics at the individual nodes, okay? Because these individual nodes, they are not static. They are not just doing sums and multiplications. They have a dynamics of their own. I say they have a mind of their own. So for example, using models like this, you cannot reproduce this kind of behavior. This kind of behavior is generated using the simulations of the algorithms I will be talking to you about, right? And they mimic some behavior you see in nature. On the left-hand side, you have a graph. You have a collection of agents. They want to get to the food, which is the green circle, but they are being attacked. So every agent has to have some individuality. They have to, to move aside if it's being attacked. And then the other agents in the network also have to observe that behavior and stay part of the group and continue to work together. So you have the situation on the left, you have the situation on the right where you have two networks working against each other. The blue network wants to get to the food location and the red network attacks the center of gravity and wants to prevent them from getting there. So this is a level of sophistication where you need more adaptation, you need more learning. You see that the individuality of the agents needs to be incorporated into the model, okay? So it is for this reason that in our work we adopt this model, okay? What we do is in the first stage, we have something that's more or less similar to the state space update, okay? You have the current state, you have at every node K, you have a current state at time n minus 1, you have some excitation at time n, and then that's going to generate an intermediate state, not the future state. And then there is a step that we refer to as social learning. The agents around you are going to look at your intermediate state, and based on that, they're going to update their state, okay? And there are many ways for you to do this, in a linear way, in a nonlinear way. I'm going to keep it simple because I want to keep the complexity simple, okay? So in this talk, I will only talk about a particular way doing it. But this is the architecture. This is the architecture, and where we added the second part, which doesn't exist in the previous formulation, okay? So let me show you, okay? Once you come up with a model, okay, to study problems of this type, there are many interesting questions that come up that we did not have in the classical single agent theory. For example, if I have a graph like this and I have an agent A on the left-hand side, you may ask the question, how should agent A fuse the information from the neighbors to achieve its objective? Okay, what weights should it put on the edges? How can it adapt these weights? How can it add links or remove links? You can also ask questions about if this network is going to make a decision, how does the information at agent A influence agent B? Or which agent had the most influence on me taking a certain decision? Okay, or if you are in the situation shown in the third graph, okay, you may have an agent there that's trying to deceive the rest of the network. So how do I identify that agent and cut the links to that agent? And many other similar questions, okay? We have written many articles on these topics, and of course also there are many other good researchers have written articles related to this topic. Okay, so for example, let me show you some examples that you can do. Let me start with this example here. I have a graph, here it is, it's connected. You have agents, you have information reaching the agents, okay? And here what I would like to do, I have a collection of data. H is the feature vector, gamma is the label. Okay, let's say cat or dog. And you have a collection of agents monitoring a certain space. And then they observe a certain feature at H, and they would like to know what label that corresponds to. Is that a dangerous situation or a safe situation? So you would like your graph to work cooperatively. You would like the agents to work cooperatively to estimate a model X star, which they can use to do prediction in the future when they see any new feature vector H. So to solve problems like this, you have to formulate, and that's what we do in our community, right? You have to formulate a reasonable optimization problem. Okay, and this is one way of doing it. For example, here, every agent, P sub k, has a cost function. What is the cost function? It's an average of loss values. Q is a loss function. So what's that? Gamma is the label you have for the nth feature. Gamma hat is the prediction for it. And you would like the difference between them to be small, or the loss value to be small. So that's what every agent wants to do. Every agent wants to estimate a model on its own that in the training data. But then you want to do it cooperatively. That's why you average the local risks over K, which are the agents. Okay? So you would like to solve a problem like this. And there are many algorithms to solve problems like this. Many different authors have come up with different algorithms. Yorgos and his team also of students, I believe Mateos and Ribeiro, Shizas and others have also worked on problems like this. So I'm going to show you the algorithms that we have been working in just as an illustration. Okay, so some time ago we came up with this class of algorithms which are called diffusion algorithms. Okay, unfortunately they have been well received, and there have been lots of follow-up research by many colleagues. And the beauty of this algorithm from my perspective is its simplicity. For example, if you're familiar with LMS, let's say, you can see remnants of it here. You see every agent in the first line is doing a stochastic gradient descent recursion. You start from the state xk and s1. You move along the negative direction of the local gradient. That's the gradient of the loss. So that's a stochastic approximation. But that generates an intermediate state, psi k. And then xk combines in a convex manner the weights of the neighbors, and that becomes the updated state, and you keep repeating. You see, the first step has the complexity of an LMS update, and that makes it very, very efficient. Okay, and then the second step is just a convex combination step that also keeps the complexity at check. Okay, so this is one kind of algorithm that you can do for inference over graphs. Of course, there are many questions you can ask. How should I choose the A's? How can the agents adapt the A's? For example, if some agents are more noisy than others, you can give them more weights or less weights. Okay, these are questions beyond this talk, but there are many interesting questions that you can ask. The first question you can ask is, does this work? Does this learn? For example, what's the mean square of a system like this? And we have theorems. For example, we have theorems like this. Okay, this is a graphical representation of the theorem. If you have a collection of agents x1, x2, x3, x sub k, you can show that in the limit, as n goes to infinity, the mean square error is of the order of the step size. So if your step size is very small, they are going to get to the solution within the step size. Okay, and not only that, the agents themselves, which is the second result at the bottom of the slide, they will be very close to each other. Little o step size. Okay, so what happens in systems like this is that the agents first learn to agree, and then they learn to discover. First they agree, and then they discover. Okay, so that you can show that that's exactly what they are doing. And they have two different rates of convergence. One rate for agreeing, and another rate for working together to discover. Okay. You can be more explicit. Don't worry about the equations here, but you can be more explicit. It's not enough to say it's O mu. You can actually find out exactly what is the coefficient multiplying the mu. And if you look at the coefficient in the second line here, it's something that depends on the Perron entries. So you can tell which agents in a graph contribute more or less to the quality of the solution. You can now ask questions like this, using expressions like this. If I want to solve a problem and I have many graphs to choose from, which graph would give me best performance? You can answer questions like this now by relying on expressions of this type, okay? So this is just an example to illustrate to you what you can do, okay, for inference purposes using graph theory like this, okay? By adding adaptation to the individual agents. So let me show you another example. So that was in the context of inference, optimization. I would like to learn something I don't know, and I would like to use it to do prediction, to do learning. Now I would like to do something different. I would like to do decision over graphs, okay? This is a more difficult problem, but you can still do it, okay, as I'm going to explain. Okay, let me give you a very simple example. Assume you have a variable theta that you don't know. Theta means it's rainy or sunny, it's safe or dangerous. Or you are observing some birds and you would like to know what's theta, what's the color of the bird that the agents are looking at. What is the object, small, medium, or large? So let's assume we have some unknown theta, and then some observations, for example, the temperature. I don't know whether it is raining or sunny outside, but I can measure the temperature. Okay, so the temperature is related somehow to the unknown. So that's the generative model that you don't know. All you have is the data, H, the observation, right? And then what you would like to do is to discover theta from H, theta hat, okay? So it's very common to assume, let's assume that I have a likelihood model. Let's assume that the temperature is distributed according to some Gaussian distribution with high mean, if theta, let's say, is sunny, and a Gaussian distribution with low mean, if theta, let's say, is rainy, right? So you assume some likelihoods. They need not be perfect, but that's an assumption. So therefore, the quality of your solution depends on the assumption. So this is a very standard formulation for those of you, and we have many good experts here who have worked like Poor and Scharf and many other experts, and also Yorgos and others who have worked on decision problems like this, and Peter here who is sitting here also. So this is a classical formulation, okay? Estimate the unknown from observations. Estimate the hidden truths from the observations. So what's the main theorem in this field? This is a very well-known theorem. Let me just state it for you. So I have observation H generated according to some generative model, which we don't know. Okay, and then you assume certain likelihoods, and these are assumptions. Okay, these are not the true likelihoods, but you assume some likelihoods. You assume some prior probability. You think that it is sunny with probability 1/2 and rainy with probability 1/2. Again, this is an assumption. So these are two assumptions that you as a designer you make. And then what you would like to do, given H, I would like to improve my belief in theta. Okay, that's the posterior. Okay, you started with equal probability, but maybe after I observe H, I think it's more likely to be raining than sunny, right? So that's the objective. Okay, let's update the posterior. How do you do it? Bayes rule, right? This is very trivial. Bayes rule. This is very well known. Okay, so what do? You do what you have on the side there, right? The prior times the likelihood. You normalize so that the result continues to be a probability vector. That gives you the posterior. This is just Bayes' rule. That's how you go from a prior likelihood to a posterior. Okay? And then you can repeat this. If you have observations arriving at H1, H2, HT, you can keep updating the posterior from time t minus 1 to time t, and then to 1 and so forth. All of this is very well known. Now, the key result in this field is the following. So if I keep updating the posterior, if I keep taking measurements of the temperature, will I learn the true state of nature? And this is the key theorem. This is a theorem, very old theorem. It says L divergence between the unknown generative model, which you don't know, and the likelihood models, which you assumed. One of them is closest to G, so that's why you minimize the L divergence, call it theta star. This key theorem says that this construction will always learn the best likelihood model that models the unknown generative model. You go to the theta star that's closest to the model. Okay, if your generative model happens to be one of the likelihoods that you assume, then you learn the truth. So truth learning will be possible. Okay, so this is a very famous result. Okay, very well known. Okay, so you go from an initial belief, if you have 4 possibilities, let's say, and you're going to converge in the limit to a basis vector. Very powerful result, okay? Now, what happens if you want to do this over graphs? I assume now I have multiple agents measuring temperatures at different locations, and all of them want to work together to discover the state of nature, or to discover whether I have a safe situation or a dangerous situation, and so forth. So I have a graph and I want them to work together, okay? Or you have, let's say, a collection of autonomous vehicles and they're working together to discover whether the conditions ahead are safe or dangerous. So this has many applications. It turns out, unfortunately, that this problem is NP hard over a graph. Okay, if you would like to find the posterior, given all the observations at the sensors across the graph, because that would give you the optimal solution. You find the posterior and then you find the maximum a posteriori value of that. It turns out that this is an NP hard problem. You cannot solve it easily. Okay? So how do we solve it? So we go from a fully Bayesian solution to what we call a non-Bayesian solution. There has been many interesting works in this domain, okay? And we have two different versions of non-Bayesian solutions. We call them social learning, okay? So again, we try to keep the structure as simple as possible. So if you see here on the first one, arithmetic social learning, you can see that the first step, every agent K performs a Bayesian update, just like every agent K performed a stochastic gradient update. So we keep the simplicity of the Bayesian update, but that gives you an intermediate belief vector psi. So that's the belief that theta is the answer, the probability you assign to theta, and then you pick the one that has the highest probability. And then afterward, the agent combines it in a convex manner on the or in a geometric manner that you see there on the right, the beliefs of the neighbors. Okay, so you have two different versions of these algorithms, and there are reasons why you have two different versions. Okay, so this is what we call the social learning algorithm. And again, can you guarantee learning if you use an algorithm, a simple algorithm like this? And it turns out that you have, and there are relative results that prove that you can. What you can show now, if you take the KL divergence between the unknown model, which is G. So now every agent now can have a different generative model because every agent is observing an observation that may have been generated differently from the state of nature. So if you take a combination of the KL divergences, of the local KL divergences weighted by the Perron vector, you can show that this algorithm converges to the minimizer. And if one of your likelihood models happens to be the unknown, then you learn the truth. Then you are able to learn the truth, okay? So that's a very interesting conclusion, that through cooperation, this graph is still able to learn the truth, even though they cannot find the fully Bayesian solution, okay? Now, the interesting thing is that we wanted to take this a step further. Like I explained before, we want these networks to be adaptive. Okay, for example, if you have a network of agents trying to discover the state of nature outside, they can work together, apply this algorithm, and they will learn. But let's assume that 10 minutes from now, the state of nature starts raining. Then that algorithm is going to take perhaps half an hour to discover that the state of nature changed, because based on interesting work from Anne and others, there is something called stubbornness, stubbornness in social learning. The agents, if they apply this algorithm as is, what happens, they start believing themselves more and more. So if the state of nature changes, it takes time for them to react to that, because they are very confident that what they have is the truth, because the theorem shows they go to the... So then we face this question, how can we modify the Bayes rule to make it adaptive? And this is a very interesting question, actually, if you think about it. Okay, and we discovered that one good way, and we have variations of this, but this is one simple way to make the Bayesian rule adaptive, meaning if the state of nature changes, the agents are going to track it quickly, is to add a step size parameter as a power, okay? So you can see that the first line is like a Bayesian rule, but it's elevated to a power, 1 minus mu, and mu plays the role of the standard step size you have in classical adaptive algorithms. Okay, so this is what we call the adaptive social learning algorithm, and then you can show that actually this tracks very, very fast changes in the environment, and the social network becomes adaptive, and it's able to track fast. Okay, and here is an example. The state of nature is changing from red to green to blue, and you can see there in the lower part, if you plot the belief vector, the highest entry is first red, then green, then blue, then green, and it reacts very, very quickly. This doesn't happen with traditional social learning algorithms. Okay, and you can do studies, and you can quantify the probability of decays exponentially with the step size. Okay, so before I move, I would like to highlight this table. This, from my perspective, this is a very interesting table, because you see, if you look at the middle column, centralized structure, if I collect data and I send it to a powerful central processor and I ask it to solve an estimation problem, minimize the mean square error, or to solve a detection problem, minimize the probability of error, it's very well known that MSE and the probability of error decay in proportion to 1 over n and in proportion to e to the minus n. There is also the famous CEO problem in information theory. If the agents share data but limited to a certain rate, how well can they perform? There are these results that you have here. The MSE is proportional to 1 over the rate and the probability of error to e to the minus r. The expressions I showed you, of course, I did not show you any proofs, but the expressions I showed you, we extended these. These are fundamental equalities that you have in these domains. To the network domain, you see that there is a very clear parallel there. The step size controls the performance. The MSE is proportional to mu, and the probability of error decays exponentially with 1 over mu. So mu plays a role similar to the inverse of n and the inverse of r. Okay, so this is a very interesting conclusion, and it has many ramifications. Okay, but I wanted to share it with you. So now let me go to the last build up on. You see, so far what I have shown you, okay, is a graph with agent, and they are linked by weights, and then they can learn. They can do inference, they can do social learning, they can do decision, okay, they can do tracking. Fine. For example, I showed you this algorithm, the geometric social learning algorithm. But in this case, we assume that the agents have some local likelihood models. They assume some models. But usually in practice, we want a data-driven solution, right? You don't have these models. All you have is data. So how can we go from the social learning context to what I call the social machine learning context, okay? So we devised system here, which we call social machine learning, okay, and for the following reasons. So in the middle you have your graph. So now we understand very well that these graphs are very powerful. They can solve inference problems, social learning problems, and they have performance guarantees and convergence guarantees. All of that is documented very, very well, okay? But we want to go a step further now. I don't have models. I don't have likelihood models. So what you can do, you can surround graph by a layer of learners. So for example, you attach to every agent a learner. It could be a neural network, it could be a logistic regression machine. And the purpose of these local learners, which you train from data, you provide to each agent data, feature vectors and labels. Okay, so this is a safe situation, this is a dangerous situation. Every agent has data, and using that data, the logistic regressor or the neural network can learn a likelihood model. That's what they are good at. They can learn the output, the sigmoidal output or the softmax output will give you a likelihood model. Okay, so you can learn the likelihood model. These are the F hats, and you feed the likelihood model into the graph and do what we talked about before. Of course, you introduce some errors when you go from the exact models to the approximate models, and you need to study how that error affects performance, and we have done that in great detail, okay, and if you are interested, there is that reference there where all the proofs appear. But what is interesting from my perspective in this architecture is the following. Every individual agent can have a different likelihood model. They can be observing feature vectors, for example, of different dimensions. One of them could be looking at the color, at the speed, at the weight of the object. So they have different likelihood models. This model by default allows for a heterogeneous model. Number two, you have the group dynamics. That's the power of the group. The group is going to work together to make a decision, even though the different likelihood models are different. And then, of course, you have performance guarantees because of decentralization. And then you have social interactions. It's much more difficult to fool a group of agents than to deceive or fool a single standalone agent, okay? And that we refer to as the wisdom of the crowd. It's called the wisdom of the crowd in the context of social learning. You can quantify these statements I'm giving you here and derive expressions that quantify how robust a system like this kind of performance it can give and so forth. Now, why do I mention this? Just to put it into context, why do I think that this is useful? You see, there is no question that there are many sophisticated AI algorithms out there, right? Neural networks, recurrent neural networks, convolutional neural networks, all of them very, very powerful. All of them, right, have superseded what humans can do in many interesting applications, especially biology and so forth, okay? However, these systems, we all know, are still prone to adversarial attacks. For example, and this is a very famous example, assume you have an autonomous car that's driving and you trained it to identify traffic signs, but then there are papers that show that if you add a little bit of noise on top of that stop sign, so that to us humans it continues to be a very clear stop sign, the machine is going to identify it as a speed sign and continue moving. This is very common in the context still of these learning machines, okay? They can be fooled, okay, rather easily, okay? Also, the results are more difficult to explain. Why do they make the decisions that they make? They can be biased sometimes, okay? So that's why I make this comparison, what I call social intelligence versus artificial intelligence, right? So if you look at this, contrast learning by humans with learning by machines. Okay, so humans, they learn from different types of data, right? You show them different types of data, speed, color, weight, different angles. Humans are very good at that. Okay, humans also are more difficult to fool by small perturbations. We are very, very robust. We tend to be very, very robust, and we continue to learn forever. And you accumulate experiences forever. You are always learning from the interactions with your surroundings, okay? And we are very good. We are social, right, agents. We interact very well with our neighbors, okay? And these are some of the features that we are trying to emulate. I'm not saying we are not there, but these are some of the features that we are trying to emulate with this architecture, okay? Add some of this social intelligence on top of machine learning or intelligence. And this is one example, and then I'm going to conclude. Just one example to show you what you can do. If you take this graph, which is on the right, and then this graph, the agents are looking at images. And this is a simple simulation just to convey a point. You see, first they are looking at the digit 0. You can see there that agent number 1 and agent 9, they hardly see anything about the digit. So on their own, they cannot tell you that we are looking at the digit 0. The same thing for the digit 1, right? However, when you put them together to work together, okay, you can see here, see on this plot on top, the social machine learning machine, it tells you that initially you were showing me the digit 0, and then around 1010 you switch to the digit 1, and it tells you with precision and with confidence, this is what I'm seeing, okay? Now, a popular method to solve problems like this is boosting, and one of them is AdaBoost, for example. If you try to use techniques to solve a problem like this, okay, to aggregate weak classifiers into a stronger classifier, you get the performance that you have at the bottom. It starts by telling you, I'm looking at 0, but from time to time it says it is 1, not 0, right? And you get many of these spikes and errors along the way, whereas the top solution is more robust and more confident about its solution. Okay, this is just an example, but we have quantified this with analysis. If you look into our papers, we have the performance expressions there to try to justify these observations analytically, okay? So what I have tried to give you, I have tried to just motivate some of the topics that we have been working on without, and there are many variations of this that we have worked on, but I hope this has given you some intuition. Okay, so there are many interesting questions that come up when you are trying to do data processing over graphs, okay, and especially when you want these graphs to be adaptive and to respond to changes in a dynamic manner, okay. So you need, for example, we can control how information flows over graphs, how agents influence each other. Something I did not talk about, we have also worked on the inverse modeling problem. If I happen to observe the beliefs of the agents, can I figure out how they were connected to each other? Okay, if I figure out the opinions you have, can I figure out where you are seated in this auditorium, for example? We have had papers on that as well, okay? Now, also we are working how to design competing networks that compete against each other. Okay, how to promote teamwork and so forth. So these are just some examples of questions that we have been working on in this general domain of adaptation and learning over graph. Okay, and there are of course many other contributions by many excellent colleagues, some of them sitting here in this room, and I hope this gives you an overview of that. Okay, so thank you. I'm going to stop here. Okay, so.
It is a very sinful thought.
Sinful? Okay.
Socially.
Oh, okay, yes.
I think that was the design. Give me 5 minutes for discussion.
Okay.
Question. So when you show the comparison of the adaptive learning, you show that you have the same role as one of them. I wonder if you know if there is a connectivity of the network somewhere in the proportionality factor. Is it? Because it might depend on how fast the information diffuses.
No,
But
you
then
are
you
right.
have this other phenomenon. You don't want people to be too stubborn and affected by the other.
No, you are right. You see, the second line, the mean square error is of the order of mu. But if you look,
also in the adaptive.
yes, exactly. But if you look at the constant that multiplies mu, it has the p's in it, which is the Perron entries. So that's the model of the graph. So the graph affects performance as well. Yes. Also, yes. Right. And this, no, this phi here, this phi has the Perron entries. Yes. I did not show it. You are right. I did not show it. Because you see, you can't, to be more precise, I should have shown it, right? I just wanted to emphasize that it decays in proportion to e to the minus 1 over mu. But you are right. There is a factor of pi there, and that pi depends on that.
Can you talk a little bit about the choice of the weights? Like, what aspects of the application influence you to model the graph? I'll choose the alphas or the weights, but the influence of one node to another. Like, how is this model?
You see, we have for example, if you start from this middle expression here, you can formulate the following problem. Assume I want to minimize the mean square error over the p's, over the Perron entries, and find out what's the optimal choice for the Perron entries to get a graph that gives me the best performance. You can solve that problem. Okay, we have shown in one of our papers actually the optimal graph turns out to be a Hastings matrix. Okay, we have shown that in some. Okay. For social learning, you can also formulate the same question, and it turns out that the optimal performance there is using any doubly stochastic matrix. So you can formulate problems like this based on these expressions and optimize over the choice of p's. Once you have the optimal p, you can construct the A that gives you that p. Yes, okay. So we have, this is recent work that we have, and you will be participating in a presentation, hopefully in a few months, right? Because you can also now ask, I told you that we have studied the problem of inverse modeling. If I observe the beliefs, right, can I find out who is connected to whom? Right? And then we have also studied the following problem. If I observe the beliefs, can I find out who has causally affected you more than other agents? We have also created an algorithm that allows you to classify the agents in terms of the strongest causal effect to the weakest causal effect over a graph. Yeah, you can find a draft about that on arXiv. If you are interested, I can send it to you. But this is very recent work, okay, so. No, that's different, your position. Yeah. Yeah, there are many different, yeah. Ashkar, yeah. Okay.
I'm also glad to see you have faith in social intelligence. I had a comment on the people that was drawing an analogy between mu and n.
Yes.
Can you
This is the problem of PowerPoint, okay? So,
Yeah. Is mu and n really the same? Because n, as you increase n, both MSE and probability of error go down. Is that the case with mu?
yeah, because the analogy here with mu, you see, as mu is much smaller, the MSE becomes small, and 1 over mu, the exponent becomes large, so the decay becomes faster. Okay, so mu is the inverse role of n and r. Yeah.
What is the role of the size of the network? It looks to me if multiple agents are collaborating, then the size of the network should play a role.
Right. The interesting thing, it's not the size of the network, it is the Perron entries of the network, the P's, and like I explained to Anna, those P's, they are, it's proportional, but there are some proportionality constants, which I didn't show. They contain the information about the graph, which are the Perron entries. The Perron entries are what codify what the graph is.
But then you have a larger network, you make it much smaller. Is that what cannot be?
No, for example, if you have a small graph or a large graph and it's doubly stochastic, the Perron entries will be the same, the performance will be the same. So. Thank you.